Right. Well, thanks to the organizers. I'm really delighted to be here today. There's a link for the slides here. So eventually I will post them on my own website, but my the server seems to be down at the moment, so I couldn't. But so Oliver kindly posted them on his site. So I encourage you to download them and follow along, because that way you can jump ahead or behind or whatever you like. If you have questions, please ask them in the chat, making it clear to I guess Oliver that you would like to ask this question, and then he'll interrupt and ask the question. So yeah. Okay. So this is related to, well, then this is joint work with Al Garver and Becky Petrius, and it is a continuation of a project that we've been working on for a while now, using quivers to understand the RSK correspondence and to extend it to other Dynkin types. And we are currently working on extending it to affine type. So the previous work, the work that's available, it's on the archive, is doing other Dynkin types, and we're currently working on the affine story. Today, what I'm going to do is I'm going to recall the AN story, which is actually the classical RSK, and then I'm going to discuss the affine A generalization. I'm really just going to be talking about combinatorics today. The third part is a few slides, just very quickly saying a little bit about how the connection to quivers works in the finite type case. I'm not expecting to get to that part, so it's there if you download the slides. You can look at it. If people want to, if there's time at the end when in the question period, you can ask, and I can say something about that if you want to ask questions about that. And I'm happy to talk to people about it as well if people are interested. All right, so to begin with, we're doing RSK. So we're thinking of mu as a partition, which I'm drawing in English notation, despite my my affiliation, which is a French-speaking university. And we think of mu as defining a poset structure on the boxes. Its top is at the top left. And we're going to be interested in fillings. And so this thing on the left here is an example of a filling. So it's just some arbitrary, we put in non-negative integers into the boxes. And I'm leaving out the zeros. So if there's a zero, I just left it blank. I find it easier to see what's going on that way. So those are fillings. Reverse plane partitions are a special kind of filling. They're fillings which have the property that they weakly increase as you move to the right, and they weakly increase as you move down. And RSK can be thought of as a bijection from arbitrary fillings to reverse plane partitions of the same shape. Okay. The classical RSK, like the Knuth version of RSK, can be obtained by taking mu to be a square partition and then interpreting the reverse plane partition as a pair of Gelfand-Sutton patterns. And so that way you turn it into, a pair of semi-standard Young-Tableau. I'm not going to say more about that. So what I'm going to talk about is a couple of ways to define RSK in this general setting that I'm using. One of them in terms of what I'm calling Greene-Kleitman invariance, so it's sort of, I don't know, maybe that's not, I'm not sure that's the best way to describe it. And the other one in terms of toggles, and I'll explain what both of those things are. And then in this finite type setting, the main result is that these two things define the same map, and it's a bijection. Okay, so let's tackle the Greene-Kleitman invariance. So given a poset and some kind of labeling of the elements of the poset by non-negative integers, we're going to define a bunch of numbers, these mu's. So mu1 is just going to be, we're looking at the maximum over all chains in the poset. That's what this is doing. This is just some chain in the poset, and we're summing up F over that chain. And so we're taking the maximum over all chains. And then for any little m, we can take the maximum over that many chains and sum up f. And so then we define lambda m to be mu m minus 1. So it's how much more you got because you were allowed to use one more chain. And it turns out that you know, so lambda 1 is greater than or equal to lambda 2 and so forth. So for example, here's this poset. This is the poset corresponding to the partition 3, 3, 3. But here I really drew it as a poset just to make it look really like a poset. And so if we were trying to calculate these invariants for this poset, mu1, we're looking at the chain here where the sum is largest, and it turns out it's this one. So mu1 is 11. When we are allowed to use two chains, it turns out that the optimal way to use two chains is not to use the first chain that we had, but to sort of rejig things around. And so we wind up with these two chains and we get 15. Then the next one, we get 16, because we can get everybody with three chains, obviously. And so then the Greene-Kleitman invariants are the successive differences, 11, 4, 1. Okay, so how do we define RSK in terms of these invariants? So we have some arbitrary filling here. And for each box along the bottom right border, which is these 5 boxes here, for each boxes along there, we're going to, so starting with this one, we're going to look at the part of the poset, the part of the filling that's above that box, and then we're going to calculate the Greene-Kleitman invariants for that. We're going to put them into the corresponding diagonal of the reverse plane partition. So here, we can, this poset just is a chain. So it can all be covered with one chain, and so we get 2. Okay. Corresponding to this box, we see, we're looking at this poset. It can't be covered by one chain. One chain can hit the 2 and the 1, but it can't hit this one as well. So we get 3 with one chain, but 4 using the 2 chains, and so we get the invariance of 3 and 1, and we put them in the diagonal here. Okay. We keep going. We calculate the Greene-Kleitman invariants here. They're 3 and 0. We put them in the corresponding diagonal, and again, and again. Okay. So that gives you one way to define, turns out, RSK. Okay. So now let me start in on the other approach that I want to describe. So this is in terms of toggling. So I'm going to have to explain what I mean by toggling. So given a reverse plane partition and a specified box, there's a piecewise linear toggle at that box, and it replaces the value that was there by, we take the larger of the entries that are immediately above it. So in this case, that's the 2, and the smaller of the entries that are immediately below it. In this case, there's only one entry immediately below it, so it's just the 5. And then we take the max plus the min minus the value that was there. So in this case, the 3 is being sent to 4. And the way to think about what's going on here is that if we know all the entries except for this 3, what do we really know about that 3? Well, we know it has to be between these two values. It has to be at least 2, and it has to be at most 5. So what we're doing when we're toggling is we're switching, so we know that we're somewhere in the interval from 2 to 5, and we're switching that interval, we're turning that interval upside down. If you were at 2 before, then this will send you to 5, and if you were at 5, this will send you to 2, and if you're somewhere in the middle, that's the toggle at a single box. And maybe, yeah, okay, so toggles commute if they are in non-adjacent boxes. So in particular, it's possible to toggle everybody on a diagonal, and you can think of toggling everybody on a diagonal at once if you want, because then you don't have to worry about the order, because if you're on the same diagonal like this kind of diagonal, well, they're not adjacent, so the order isn't important. Okay. There's a couple of, this is maybe not super important, but it's somehow, I mean, it's helpful to think in these terms. And this turns out to be even more helpful for some other elements of our project, which I'm not going to be getting into today. But but let me just say this anyway. So we want to think of the boxes below the shape as really being filled by infinity. And notice that makes sense because this is supposed to be increasing as you move downwards. So infinity obviously could go in under any reverse plane partition. We could have a bunch of infinities here and we would still satisfy the reverse plane partition condition. And so let's think about what happens if we toggle here at an infinity that is just below the reverse plane partition. And what we want to do is we want to say, well, so prosaically what we want to do is we just want to say we want to replace this by the larger of its two neighbors above it. But this is correctly calculated by just applying the formula from before, where we say it's take the minimum of these two guys, well, that's infinity, and the maximum of these two guys, that's 3. And then I'm going to subtract the value that I had there, which was infinity. And so I get infinity plus 3 minus infinity. Oh, yeah. And so I get the 3 that is what I wanted.
So Hugh, there was a question in the chat from Monica, whether these toggles are related in some way to mutations of cluster algebras.
So these are piecewise linear. There's a, so yes, I mean, the answer is yes. You can detropicalize this, and then you have some, and then you have something that looks more cluster algebraic. I think that I mean, it's not obvious what the connection is. Arkady-Berenstein has told me that there is a connection, that it's some kind of monomial change I don't know how to make, I don't know the precise statement, but yes, it is cluster algebra-ish for sure. Okay. The other thing that I wanted to do is just to say we can also put zeros around outside the RPP, but sort of extending off to infinity, and that doesn't cause any trouble. If we try toggling these guys, they'll just always stay as zeros. Okay, so it's not that important. Anyway, so how did we define RSK in terms of toggles? So there's kind of an induction step where we suppose that RSK is defined for some partition, and we want to define it for a partition that includes one more box. So in this case, we're supposing we already have figured out what the RSK for 3.1 is, and we want to figure out what RSK is for 3.2. So the way we do that is we take our filling of shape 3.2, and we just forget the box that isn't in 3.1. So now we have a filling of 3.1. So we can apply RSK, and we get this guy. And then finally, we have to do the interesting step is, what do we do now to get up here to find what the RSK for 3.2 is? And so that step is we toggle the whole diagonal of that box that was in nu prime but not in nu. So we toggle that whole diagonal, and as we saw before, that adds in this box, that makes this box become part of the shape. In the sense that it goes from being something labeled infinity that we're ignoring to something with a numerical value in it. And so that would give it the value 2 when we do the toggle. But then we add the value that was in the filling. So in this case, we add 1 and we get 3. So that's the toggly way to calculate RSK. And so you can use this to build up, to find the RSK of any filling, just by sort of starting with the empty partition, going to the empty reverse plane partition, and just as a sequence of toggles. So we toggle and add, and we get this 1 here, and then we're going to toggle here and that gives this a 1, and we add 0. So even though there was a 0 here, we're still adding. Interesting things are happening even at boxes where there wasn't anything in the filling. Next, I think I'm going to toggle here, and so the toggling is going to put a 1 here, and then like that. Here we're going to toggle next. And so we're going to toggle here, and we toggle here as well, because we're toggling in this whole diagonal. So we toggle here, and we add this 2, and that gets us a 1 here, and that gets us a 0 here from the toggle as well. And then we just keep going, and there we are. And you might recognize this because the result is that these two definitions agree. So this toggly definition has a very dynamical algebraic combinatorics flavor. So, it's fun for people who like that kind of thing. The Greene-Kleitman invariant version also seems really natural. And so the statement that they agree goes back to Kirillov-Berenstein. And Sam Hopkins has nice notes on his webpage, which was where we learned about this initially when we were starting on this project. Okay. So that's the that's the AN story. And now I'm going to explain how to do this for AN tilde. I see that I'm less, yeah, okay. So I'm going to explain how to do it for AN tilde. Right. So first of all, I need to tell you what the poset is that we're dealing with. So what we're going to do is we're going to choose a lattice path with A right steps and B up steps. In this case, it's just this path here, just right, up, right. And then we're going to take all the AB translates of that. So we're going to take this path and then this translate of it, and then there's another translate of it, another translate of it anyway, and going off in both directions. So this is now this piecewise linear path that divides the plane into two pieces, and our filling is going to be above this line. It's going to have a finite number, and it's going to be periodic with respect to this AB translation, and it's going to have a finite number of orbits of non-zero entries. So here you see like this 1 and this 1 are in the same orbit, so they had to be equal, and the 2 and the 2 had to be equal. Okay, so those are the fillings. The reverse plane partitions, it's the same kind of story. They're above the path. They're periodic. They weakly increase down and to the right, and they have only finitely many orbits with non-zero values. Okay, so the same story. And in fact, what we're going to see, the next thing that I want to tell you is something that you are not going to be surprised about at all, because basically I'm going to tell you two definitions, the Greene-Kleitman invariant definition and the Toggly definition, and they agree. So that maybe I can just skip the next 3 slides or 4 slides or something, but I do want to just walk you through it, but it's kind of not a big surprise, I think. So for calculating the Greene-Kleitman invariance, we're just for each box again on the border, we're restricting to the part of the filling that's above that box, and then in the corresponding diagonal, we're entering the Greene-Kleitman invariance. And of course, you don't have to do an infinite amount of work to do this. You just have to do one period, and you're done. So here, what we see above this is really just this 2. That's all we see. And so the Greene-Kleitman invariants are just 2 and then infinitely many zeros. And so we get 2 and infinitely many zeros and 2 and infinitely many zeros. And over here, same thing. Over here, it's a little more interesting, and you start to see that the periodicity is doing a little bit more here, because I mean, this 1 here is seeing both of these 2s, even though they are kind of the same 2, in that they're not this being a 2 implies this had to be a 2, but the 1 sees both of them, and so they both are relevant, and they both contribute. Okay, so that gives you a definition. There's also a Toggly definition, and again, it's very, very similar. So the inductive step is we have these two lattice paths with the same number of right and up steps, and they agree except that there's one box below P prime that's above P. And suppose we already know how to do RSK for P prime, then we get an RSK for P, by applying RSK for P prime to the part that's above. Sorry, it says above P, I meant above P prime. Then we toggle along the diagonal, and then we add the entry in that box to that position of the reverse plane partition. So it's the same thing as before. And again, you can use this to get an inductive definition. In this case, we can't go up to the top. In the finite type case, we could go up to the very top, and but we can't do that here because there is no very top. What we can do though is we can go up far enough that everything above it is 0. And so if we just decide that the 0 filling goes to the 0 reverse plane partition, then that gives us a starting point, and then we can induct from there. So we did that in this example. We start off with this shape, with the line shown in red, and above it is 0 in the filling, so above it is going to be 0 in the reverse plane partition. To begin with, it won't stay 0 because we're going to be doing these toggles. So now we're moving down into this step. We toggle and we get 0, and we add 2, and now we get 2s here. Now here we're toggling and we get 2s as a result. We also toggle here, but we still get a 0 there. Finally here, we're going to toggle and we get 2s in both these positions. And then we also add this 1, and so we get a 3. And we get the same thing as before. So the two definitions agree. The thing that I find a little surprising is that this isn't a bijection. So there's a couple of things that we could do to make it bijective. Right, so why is it not a bijection? Well, let's look at this reverse plane partition. If it were a bijection, we would expect to be able to reconstruct what filling it came from. How do we do that? Well, we look at some bottom corner and we say, we look at this guy and we say, well, how did this get here in the reverse plane partition? We look at this and we say, he's actually equal to the larger of his upper neighbors. So we didn't add anything at the very last step. So all we have to do is untoggle. Whoops, no, I'm sorry. We have to untoggle. And now we know that there was a 0 in this position over in the filling. Great. So we can just keep doing that. We look at this position. We say, well, did he come from, was there something there? No, there wasn't anything there either. It was also a 0. It was also a 0. And we untoggle and we just keep going like that. But what we realize is this never goes away. As you keep working this upwards, it'll just stay there for good. And I realize I'm out of time. So
you've got 5 minutes, Hugh.
I do.
Yeah, we started late.
Oh, super.
You're okay.
Oh, fantastic. Thank you. Okay, great. So what's happening is that this this is just like this is the border itself that is filled with 1s, and as we toggle it going backwards, we're just staying. We always have a reverse plane partition whose border is filled with 1s, and that just persists. So obviously that didn't come from any filling under this RSK map. So there's 2 ways we can make RSK be bijective. One way is to describe the image as a subset of the reverse plane partitions. So to do that, what we do is we look at the reverse plane partition and we divide it into layers by taking our path that defines the reverse plane partition and then taking its translates upwards. And so a filling is in the image of RSK if and only if, for each pair of successive layers, there's some position where there's a box in each layer where there's actually an equality. So that's the condition. And you see that that wasn't satisfied in that previous example because we had one layer which was all ones, and the next layer up was all zeros. So that agrees with the fact that that wasn't in the image. The other.
So Mike asks on the previous slide, if you toggle where that 5 is, does that turn into an infinity?
If you toggle where on this slide?
I asked that a long time ago. Did that just show up now?
Oops, it did just show up for me, but maybe there's just problems with the chat still.
Yeah, because that must be why everybody like posted that link like 10 times because it wasn't showing up right away. I wasn't yeah, you can ignore my question. I was confused with when you do the stuff with the infinities, but.
Oh, okay. Yeah, okay, maybe we'll come back to it in the questions if it's still a question. Okay, so yeah, okay, so there's so we have an equality here, we have an equality here. So this is an example of something that could come from RSK, that does come from RSK. And the other thing you can do is you can say, well, you could say, well, I like all the reverse plane partitions. I don't want to get rid of any of the reverse plane partitions. And so I want to increase this set of fillings somehow to account for the extra information. And so it turns out what happens if you run this process backwards is that eventually it stabilizes and you just get this thing that's persisting, like that example that we looked at. And at that point, that remaining filling is constant on the layers. So you can just describe it by a partition. You just record you record what's in the bottom layer and then what's the next layer up, what's the next layer up, what's the next layer up. So what this then amounts to saying is that this RSK defines a bijection from a filling together with a partition, which is remembering what sort of the persistent part is, and that bijects to actually all the reverse plane partitions. Okay. So, thank you.
Thank you, Hugh. So I don't know what's going on with the chat. Per asked if there's a Q analog.
We are also interested in thinking about like Hugh Whitaker's. It doesn't, so that's one thing you can do instead of saying I want to do RSK is you can say, and you can think of RSK as like a Cauchy identity for Schur functions. You can instead say, I want to do a Cauchy identity for Q Whitaker functions. So I and another group of people, postdocs at UCOM now, have been thinking about that, and also trying to go further than that. But that isn't really in a state to be talked about just yet.
Anna Schilling asks if you can do something analogous for K-theoretic insertion algorithms.
I don't know how to do that. I also don't know what. Oh yeah, okay. I guess there's a okay. So there's a reasonable. There's a good question, and I mean in this case. Kind of the two the recording tableau and the insertion tableau kind of get folded into this one object that is the reverse plane partition, and I'm not sure how that would work in the K-theoretic setting, because there I think those two objects are kind of qualitatively different. I mean, I don't know, maybe that's not important, but that's the first thing that kind of comes to mind as a thing that suggests that the story might be different.
And then several people also want to know how this is all related to the affine RSK of Shimutov and Piliavsky and Yudovina.
It seems to be quite different because our periodicity is kind of perpendicular to the direction in which the poset is increasing, but for them, the poset is increasing in the direction in which they have periodicity. And so this means that they have this means that they can't literally do things like take Greene-Kleitman invariants because the answers are all infinite. But because our periodicity is kind of going in the opposite direction, we can have finite answers. So at least, I mean, that's what I understood from what's in. That's what I understood. I mean, there may be something else to say as well beyond that. I'm interested to, yeah, I would love to see what there is in the way of connection.
Any more questions for Hugh? The chat's being weird, so I may just have not seen your question, in which case maybe just unmute yourself. Here's a question from Pasha. Pasha says, Pasha, maybe can you just say it yourself?
Sure. So this is from the slide. I just want to understand the left side of this. So what does it mean, product of fill P and partitions?
So this just means that what corresponds to a reverse plane partition is a filling together with a partition. So the idea is that you take your reverse plane partition and you undo the RSK, and what you'll find is a part that turns into a filling, and you'll find this sort of persistent part that never disappears, and that part that doesn't disappear is naturally encoded as a partition.
Okay, I think I understand.
Okay, I mean we can definitely chat if you'd like later.
Okay, so in the interest of time, let's awkwardly thank Hugh again for a great talk, and we'll resume in 5 minutes for Carolina's talk. We're gonna push back the brakes for a bit.
Thank you all very much.